Actually, like the question is whether I'll post lecture recordings. I was actually posting and somehow maybe my Git workflow failed or something failed on push and I didn't notice, but they didn't go through. But ideally, I should. The plan was to have everything posted on the website. There is a couple of other like right here, but somehow the push didn't go through. Yeah, it's everything is on YouTube right now, but I'll post everything on the class web page. But also, I should say that I screwed up the numbers. So I was actually thinking that the only number which I have for this class is 5965, and that's an undergraduate number. But really, and you already knew it, but you guys are still under this old number 6465, which is probably correct. So I will probably move the website from 5965 from here to 6465 and post the schedule and all the lecture recordings here. So I apologize.
Dude, it's been so long. How you doing? Dude, guess
Uh,
what? I'm in my class right now.
mute,
No,
mute.
you're good. You're good.
Who else? Yeah, everyone else is probably muted. Uh, so okay, so that's coming. I apologize for that. What else? Any other questions? All good. So okay, so today our plan for today is figure out. I checked in the only one, first one posted. Alec, can you actually like okay, let's come back to this later. But the plan is to post everything essentially, and feel free to unmute yourself and ask a question. Don't have to use chat. That may be might be a little bit more interactive. Okay, so the plan for today, just quickly draw what's going on here, is to learn how to boot into Rust to make sure that we can essentially assign a homework and start working on it. So like what's going on here is the following, right? So remember our plan is we wanna build something like a tiny microkernel. That's our microkernel. It runs in that's like it runs in ring 0, similar to x86 kernel. Everything else runs as user process. So essentially, um, everything else runs in ring 3. Each process will have its own address space, right? So it's P1 and P2. And like according to the microkernel tradition, device drivers will also run as user level processes. So for example, if we have something like a net device driver, then it will talk to a real physical piece of hardware, but it will run as a process, and other processes will be able to talk to this net device driver through an IPC mechanism. So this is inter-process communication mechanism by sending and receiving a message, right? And the idea, like, and that's of course, it makes total sense, is to build a system which runs on multiple CPUs, similar to how x86 was running. So, like, if you have core 0 and core 1, then like you obviously boot on core 0, but then similar to how x86 does it, we will start other cores and boot on those other cores as well. And essentially each core will have its own scheduler. Everything will require some inter-process synchronization, similar to how spin locks were working in x86, right? But that gives us a blueprint for kind of a very reasonable operating system, right? So if you have a modern piece of hardware, be it like an ARM chip, which you use in your phone or some embedded device, most likely you'll have to deal with multi-core systems, right? And also we're going to target x86. So essentially, x86 64-bit hardware, right? So x86 itself was designed for x86 but 32-bit hardware, and instead of like moving to 64-bit hardware, the authors of x86 moved to RISC architecture, but we're gonna stick to x86. And if you if you learn how x86 works, you will be able to equally well code for any other architecture like ARM. But essentially, that's the plan, right? And the deal is that we write this microkernel in Rust, right? And these user processes, as they run in Ring 3, they technically speaking can be written in different languages. And maybe for the fun of it, we can try to run them in C, right? Or in something like that. Or maybe we can write them in Rust as well, right? It doesn't matter, because here we will have page tables and we implement this address space, which I'm drawing here, as a hardware mechanism, which will be isolating untrusted user code from the trusted microkernels. Essentially, all communication here will be through syscall, right? So this overview makes sense. I just wanted to make sure that we all are back on, we're understanding everything together in the same way. Any questions? All good. So, and what we're gonna be doing for this for today's lecture, for sure, is we're gonna be using Philip's blog, which talks about how to boot into Rust. So, however, there's a couple of things here. So first of all, right now the public edition of a blog is edition 2, and that's fine. But he also has a edition 3, which is updated to kind of reflect better the changes in the Rust toolchain, right? So what I'll start teaching edition 3, and it will help us to get running on modern Rust, stuff like that. Then we switch back a little bit to edition 2, cover certain topics, but we're not going to really implement what Philip is implementing in his blog post, right? So I had a couple of students who said, okay, are we okay working through his blog posts, because Philip talks about how to build an operating system? And I sure said, yes, fine, but most likely our trajectory through this operating system design space will be slightly different. So today's lecture, and maybe just a bit of tomorrow's or Wednesday's lecture, will cover bits of material which are covered in Philip's blog post. But after that, we kind of switch and we'll start building our own stuff, right? So, and also Philip slightly puts different accents on what or emphasis on what is important. Like he starts booting or on a newer firmware interface, EUFI. We probably not going to do it. We will just be using multi-boot similar to x86, and he spends time rendering in the frame buffer. We also don't really care about it. So for us, serial line is enough, although today probably I'll show how VGA frame buffer can be used. But it's fine. If you want to build it, and it's honestly a minor effort, that's totally fine. We'll also be using a slightly different build tool chain. And again, there are like ups and downs of what is happening here. So just like, I mean, it's like you can build different, you can build the kernel different ways, in different ways. Probably doesn't matter. There is no real argument that one approach is better than another. So I would be like, I cannot say that there is a strong argument, but just a little bit easier for us as system designers to build whatever I'll show, I guess. Okay, so okay, so our goal today is essentially learn how to boot into Rust main function, right? Any questions about it? Like for now. Okay, let's get going. So my thing is this. So I have like not this. I have a couple of things here. So not this one, this one, not this one. Among these four screens, I will open them all. I still don't know which ones is which. Not on this screen altogether. That's okay. How do I find the right web browser? Cannot find it. So we'll do, no, let's do localhost edition 3, something like this. Random link here.
Hey, I sent the link in the chat, by the way.
Send a link to the chat. Yeah, that's fine. I just want to run a rendered version, so like which I have here, one of my wonderful shells as well. So what is that? I'm just because Philip occasionally uses he uses images, right? So and you can read Markdown, which is totally fine, but in the end, if you wanna have a better, like, if you want to understand the images better, it's a little easier to get a rendered version and look at it. So so what I have here, just to explain you, so Axel is total, or whoever was saying, probably it was Axel, but I was thinking Alex, no, Axel. Yeah, Axel says, okay, look, guys, I sent a link to a edition 3 version of the Philips blog post, and what I have here is that I just ran Philips website generation workflow, and I'm rendering it statically as a for a web server. So that's why I'm like opening it locally. But mostly the only, what is it? Sorry. To make sure that we actually navigate to the right version. Here we go. What is it? Yeah, so something like this. So essentially, that's the right way to go about it. So I have not all the blog posts are updated, so only like the beginning is here. But okay, so we start with this one, minimal kernel, and essentially I'm opening this blog post from Philip. It's a third edition of his web post, and it teaches you how to essentially boot into Rust. And we talked about it last time. The main idea here is that normally when you build a Rust program, the compiler assumes that you are actually trying to build something for the operating system which you're currently using for building, meaning that if you're building on Linux, it will try to build a Linux executable. If you're building on macOS, it will try to build a macOS executable. And it also assumes that all the operating system libraries, like essentially a standard library of the language, which relies on libc, is available, right? And of course, and what does it mean? It means that all the functions like printf, or printline are available, right? Because they use operating system interface to pass this data to the operating system kernel. The operating system kernel either draws it on the screen or puts it on a serial line. And the very first thing where you want to build your operating system is to say, look, by the way, since we're booting on bare metal, so nothing is available, right? Whatever the environment which I will be running in, I have to create it, right? So if you want to build your a function which print something on a screen, like on a VGA or on a serial line, fine, you have to write this function, and this is what will happen today. But in order to make sure that compiler is not complaining about, you have to build something what is like what Philip is calling a freestanding executable, right? So the executable which does not depend on a standard library. And a similar thing we did when we were working on the homework for the undergraduate OS class. We said, okay, look, guys, we're going to boot into C, and we used a collection of make files, a tiny assembly file, which essentially enabled segmentation and paging, and then setting up the stack, and we were running inside C. And something very similar has to happen here, right? So the main idea is that, let me go switch back to this, to my diagram. So I will scroll down. So the main idea is that what we're going to be doing, we will generate Rust. We'll use a Rust file, which will have something like, I don't know, Rust main function, right? And like it's not the main function, but that will be used as an entry function, and that will be the main function of our kernel. But in order to get to that function, we will be using, similar to how we did it in the previous class, we will be using some kind of a boot ASM file. And specifically, this file gets control from the bootloader. And then it will be, we'll set up, like essentially we'll enable segmentation. And specifically, we want to switch to 64-bit mode because we will be, as a bootloader, and again, Philip doesn't do it, but it's kind of like meaningful. As a bootloader, we're going to be using Grub. It's an open source bootloader from Free Software Foundation. It boots on all sorts of hardware. It's not ideal, but it's good enough. Grub leaves us in 32-bit execution mode. So it's different from actually how x86 was booting, because x86 was essentially implementing a boot protocol with the bias. So it was using 512 bytes in a master boot record. And we're saying, okay, we don't care about those details because, okay, now we're building a real kernel. So we don't care about learning how, like we do to a certain degree, but it's like a whole different pile of worms and we don't want to touch them. We let Grub and people who want to work on bootloaders help us. Grub starts on the hardware. Typically you see Grub menu if you boot it like any server or like Linux systems, right? But essentially, in order for the Grub to boot our system, we implement something what is called a multi-boot protocol header. It's essentially like a header which allows Grub to recognize that we are a kernel, and after that it passes a control to us. We will use a sequence of assembly to enable segmentation, enable paging, and essentially set up the stack like we did for the x86 thing. And then after that, essentially jump to our Rust main function. Inside this Rust main function, we're not going to be doing anything today, but essentially what we're going to do is that we say we want to print something on a screen. And essentially for that, we will build two device drivers, which we borrow from Philip. One device driver is for the VGA console, and a second one is for the serial line, right? And like again, VGA is more of a luxury. I guess who cares? We're not going to print anything on any screen. Like, yeah, sure, if you want to build in real hardware, you can do it. But we, for our grading purposes and everything, we will be just using the output of a serial line, right? And that's how we run stuff in a data center, because we never have access to any screens. When you're building a real operating system, real meaning like a research prototype, which does some testing on a data center hardware, serial line is typically enough. Although, of course, like I should step back. So maybe there are use cases where you really will be printing something on a screen, right? Which is probably possible, right? So, okay, this outline, is it clear? Or let me stop for questions right now. All good? So essentially, a high-level idea here is to make sure that when we compile this Rust code, it knows that there is no standard library available because we're not running on any operating system. And essentially, if you want to have a print function, then you have to build it yourself. And I'll show you how. Okay, so back to Philip's blog. So, okay, for sure. like Philip tells you, if you want to start a new Rust project, do this, like cargo new edition. We're not going to do this. Instead, we will be using hello OS. So like this is a tiny repo which I'll give to you. So essentially, it has a slightly different boot chain because we borrowed it from a couple of other operating systems which we built. We like it a little bit more. It's driven by a makefile. We'll come back to in a second. So essentially, this first line, like you can kind of skip because we'll never use it again. But what's important here is that what Philip tells you, that the way to convince the Rust compiler that there will be no standard library is you need to add this no std attribute to your Rust file. And okay, sure, then if your main function in that, like if you follow these steps and we created one main rs file, then you're trying to compile it, Philip says, okay, we've said no std, you do something like cargo build, it says, okay, by the way, I don't even know what this print line function is because, well, standard library is disabled, so print is not there. So, and actually print line is a macro, so this macro is not available, so it bugs. So what Philip suggests you to do is says, okay, sure, just comment it out, have an empty main function for now. After that, you run cargo build again. In our case, we just run make in the make file. I'll show you in a second. What you will start seeing is that, again, the compiler says, by the way, the panic handler is missing. And the idea is that it's also part of this Rust runtime, minimal Rust runtime. So when the code panics, the compiler promises to invoke this panic handler. And again, we've built operating systems which had real panic handlers, and we'll come back to it maybe. But for now, just to get going, we're not going to do anything. Panic handlers, for example, you can say, you might try to recover from a panic. Maybe the page is unmapped, maybe something else, maybe the condition is not mapped. Page is unmapped is a little stretch. So really, I guess that then you will get an exception instead of a panic. But you can try to recover. But essentially, what Philip says, the next step is to just add an empty panic handler. This one is a function which just takes this panic info as an argument and then does nothing. So it just loops forever. Sure, but that's part of this sequence of how to essentially boot in bare metal Rust, right? The next step, okay, you have a panic handler right now. Rust allows you to unwind fault exceptions, right? And the main idea in Rust, like in C there are no exceptions, but in Rust there are. So the idea is that your unwind handler can walk the stack and essentially call the drop methods for all the objects which were allocated on the stack are still alive. So for example, you might say, okay, does it always make sense to do it? So maybe your drop method will correctly close a file in a file system, or maybe even like flush the file or something along those lines. Again, in kind of a research domain, the usefulness of these panic handlers is a little debated, meaning that, like, if I understand correctly, for example, you're not even guaranteed to deallocate even all the memory in Rust, because due to cycles on the heap, you can have cycles between the objects, and the panic handling doesn't even guarantee that you will deallocate all the memory. Although we should probably I should be careful saying it, but sure. But in our case, whatever, unwind mechanism is not there anyway. And what we're gonna do, what Philip suggests to do, is to say, by the way, there is an alternative approach in Rust. Rust allows you to simply abort the program, right? And sure, so in order to do that, in this cargo.toml file, you just say that for both development and release builds, the panic approach to handling panic is just simply abort, right? So, and that's fine. After that, essentially, your stuff should start building, right? So what we do here is we said, okay, got it, we disabled, we said no STD, we said, we implemented a simple panic handler, and we said, okay, do not unwind the stack, just simply abort. So 3 things. After that, it builds. Right now, what we have is that typically the compiler will start looking for the start symbol. And in order to convince, since we don't have a start symbol, at least Philip doesn't, in his case, it's main. What he suggests to do is just to like, there should be a flag saying, essentially, you should just say something no start. I don't know what he says here. Okay, we saw it slightly different in our build, so maybe I shouldn't like stop too much. But essentially, what he does is that what he talks about then later is that he says, okay, if you try running the cargo build, it will try to essentially figure out the target for which compiler tries to build the executable, right? And typically the target might be something like a Linux system with a specific, whatever, 32-bit or 64-bit executable code, right? So in order to build for this bare metal executable, there is this new target which Rust compiler supports now. So it's x86_64 unknown noun. And specifically this this non-prefix indicates that there will be no underlying operating system, right? So Philip says, okay, just use this Rust up command to create this target, and essentially after that he says, okay, you'll be able to like add this no main attribute. So essentially like essentially it says do not normal entry point. I do slightly different, so I don't really know how Philip does it. So he says, okay, look, okay, his solution is this, and this is kind of similar to what I'm doing. So what he says is that if you add this attribute, it instructs the compiler to like do not expect the main function as an entry point, because typically the idea is that you first execute certain code before even the program main starts, and then like jump to main, right? And here, like he says, okay, instead it says, okay, tells the compiler to not expect this the main entry point, instead expect the start, and it's with underscore start entry point, and that will make the compiler and the linker happy, making sure that the linker will know that there is a start entry point, and so it will link the executable in such a manner that the bootloader will invoke this entry point, right? And essentially, in order to make sure that the symbols are not obfuscated by the compiler, you have to put a no mango attribute here, making sure that the symbol is preserved as it is. And also it's like to make sure that it can be called from the assembly. So we put this extern C attribute, which ensures that it uses the C calling convention. So kind of the same calling convention which we were using in x86, but instead of 32-bit convention, the compiler will use a 64-bit convention here. Let me stop here for a second. Does this make sense?
Wait, so the idea is like we initially jump to start, and then from start we initialize some things, and then we jump to main. Is that right?
Correct, right. When you run on Linux, right? And on Linux, there is a ton of stuff running before main, and not only on Linux, but just even like it depends on which language you're running, obviously, right? On like C, for example, has support for running constructors. Like you can be surprised that C has constructors, but it does have them. And so like I don't exactly remember all the details. I used to know them better, but yes, typically there's a ton of stuff running before the main function starts executing.
Thanks.
And again, so in practice, you can bend those rules quite a bit, but like Philip kind of like tries to connect the dots in the most with the shortest path. But I'll show in a second how my build does it and how I recommend you to do it. But I mean, I'm not going to insist. If you want to use Philip's build system, go for it. I still kind of, when I said I do not insist, I probably do insist, because like his overly simplistic approach will kind of, I mean, everything is possible. I mean, you can do whatever, but the way he does it, it will complicate things when we start booting on multiple CPUs and stuff like that. You'll see in a second, like if not today, then on Wednesday, that it makes sense to run a short assembly sequence before even jumping to your first Rust function. It's just easier.
Professor Rutzev,
Yep.
are we talking more right now about like the specifics of our build system, or are we talking about like Grub has handed the reins over to us, and these are the steps that need to come next, chronologically?
Kind of. Okay, so what we're discussing right now is that, let me explain. That's probably a good question, and I appreciate you. We want to, by the end of today, it's like we want to have an executable, like a binary, which at the very top has a something what is called a multi-boot record. I'll show you what it is, and we've seen it in xv6, but maybe you didn't pay attention because I never emphasized it, right? This binary will have a start label, and the way I want to do it, and I recommend you to do it, is that this code is generated from some assembly file in my build at boot.asm. And by the end of this sequence, you will jump to this, to the very first Rust function, which in my case will be called Rust main. Although it just, the name doesn't mean anything. It's just like, I wanted to call it Rust main, right? And so this code is compiled from Rust, right? This is compiled from assembly, right? And we're going to be using a grub bootloader. And grub doesn't care at all. What he cares is just this thing. It says, okay, guys, I will take a look that this has a multi-boot record. And then I will just, if I remember correctly, I forgot which format it uses, but it understands that the entry point is the entry. I would say, I should actually, this is surprising that I don't remember, but I would imagine that this is an ELF, but maybe I'm wrong. And essentially it says, okay, look, guys, I will check that this is a multi-boot record, which means that it's a valid kernel in grub's view. And after that, it just passes control to start. And after that, we control everything. So this is kind of what we want in the end. And what I was trying to explain is right now is how to generate this part from Rust, right? Because normally Rust will try to compile against the standard library. It will try to put the main function as an entry point, and then maybe the runtime against which it linker will link it will call this main function. But none of it exists right now, because we say, look, there will be no runtime, nothing. We like what grub will just pass control to this start. In effect, this will be our like runtime, which will set up execution environment for Rust, right? So for example, we will set up a stack here, right? And so in order to but this is just roughly speaking, an ELF file, which the compiler generates, right? We trust the Rust compiler to generate this ELF file. And then we're gonna link against it, right? And what we're trying to explain to the Rust compiler, so please generate this minimal, we want to have the Rust code. So this Rust main function should be eventually converted from Rust to executable code, right? But in order for us to convince the compiler that we want this kind of standalone executable, we say no std, trick number one. Then we define our own panic handler, because when there is no std, the panic handler disappears because we said no std. Then we say no unwind, and we said no main, right? And after that, the Rust compiler will be just happily, essentially, if you do those trick, and that's essentially what I was trying to explain today, that these 4 things are required and nothing else, more or less, right? After that, we will get this executable binary out of Rust, and it will be ours, and we will use a linker trick to make sure that we're gonna link this thing, which is our kernel. And we will flush it to disk. Specifically, we will be using ISO format, kind of like an optical disk. And then the grub will just load it in memory, and we'll start pass control to this start entry point. Make sense?
Yes, that makes sense. Thank you.
Any other questions? Ask the questions. I mean, I didn't I get it. So I was jumping between multiple screens, and I was talking about Philip's blog post. And the reason for that is that I want you to read his blog post as a homework. It's part of building the homework. But on the other hand, I don't want you to just blindly follow his posts, because we're going to do stuff slightly differently. So it's kind of close to what we're going to do. And you have to get this conceptual understanding of what's going on. But still, it will be a little different. So more questions.
So
Yeah, go ahead.
you hear me? Sorry. So most of what we do before we step into Rust main, as we're calling it on this presentation anyways, is mostly just configuring the hardware and any infrastructure that we need in order to actually go to main.
No, not exactly. So we don't. Okay, maybe I misunderstood what you're trying to ask. So you're asking is, what is that we're going to be doing in this boot asm, right? Is that what you're asking before we jumping into Rust main?
Yes.
And I don't know, Alex, were you in my undergraduate?
Yes, sir.
Yeah. So do you remember the homework, boot into C?
Yes, sir.
And so we did this in this boot asm. Remember, we set up the segmentation, set up the paging, then we set up the stack, and then we call the main function, right?
Yes.
And from inside main, we printed on a frame buffer saying hello world or something like that, right?
Yes.
So this is very similar. So it's just that instead of using C compiler, we're using the Rust compiler in a Rust language. This boot asm is conceptually very similar to what you've seen in your homework last time. And the build system which we will be using will be kind of similar to what we were using in that homework. It will be a makefile and a linker script. But since we're building Rust, we will be using cargo as well. And cargo is this thing which is like a stock way to build Rust code, right? And I'll show you in a second. But conceptually, yes, we're going to set up the page tables. The only difference is that in our homework, we were starting, I forget exactly, but we ended up in 32-bit executable code. I apologize. COVID gets me, so now we'll be, just a second. Yeah, but here we'll be doing 64-bit code. And so we'll set up the page tables and the environment slightly differently. And of course, since we are now dealing with Rust versus C, in C, I apologize. In C, it was much easier to like, I mean, it's pretty easy in Rust as well, but you have to tell the compiler that no STD, define your own panic handler, disable stack unwinding, and say that there will be no main, so it doesn't get confused.
Okay, that all makes mostly perfect sense to me. So thank you very much.
Yeah. Anyone else?
But, I have a quick question here. So if my stack would be set up during the boot.asm, why do I need to like do no unwinding of stack in my Rust main?
Right. So no unwinding is different. So Rust, like imagine like talking about like a regular Rust program. Forget about the operating systems for a second. So there was some function, let's say even main called foo called bar called bars. As a result, you have a stack. Imagine it grows down here. Some of this belongs, like the stack frame belongs to main. Then foo belongs, like this part of the stack belongs to foo or created by foo. Like this is bar and this is buzz. Sorry for the handwriting. Honestly, I swear like last year it was a lot better. And imagine inside buzz, panic happens, right? Panic in Rust can happen, for example, you have an array A and you accessing array out of bounds, right? So Rust does a check and says, okay, look, guys, it's out of bounds. What are you going to do now? Like, what's the meaningful, okay, tell me, what is the meaningful way forward from accessing an array out of bounds?
Yeah, so it's just an error and then like, um, I guess the error needs to be handled wherever the try catch is defined. So like wherever I'm handling, so if my say try catch block is in the main, it'll have to go all the way to the main.
Correct.
Like yeah,
And as part of this error catching, apologize. Imagine you had some objects allocated on the stack, right?
right. They'll need to be deallocated.
Yeah, and so when this panic happens, Rust compiler says, okay, got it. I'll pass this stack frame to the unwind handler. Sorry, okay, for this. Unwind handler. And the unwind handler will be, it has enough information, debug information to unwind the stack. So essentially it says, okay, I actually know that this is an object of type A, and I will call the drop descriptor for object of type A. And this is an object of type B, and this is C and D. And it will be moving, like it knows where because remember in x86, we were using, what is it called? What's this register? The stack frame register. Jesus, I forgot. So stack pointer and what is the ESP?
Pointer?
Yeah, bottom pointer, correct. And so we said, okay, to make it human readable, we will be using bottom pointer and we'll be maintaining the stack frames, right? And here in Rust, obviously, like people say, look, we're gonna be shooting for the last bits of performance. So this typically Rust will not maintain the frame pointer. And instead, it will generate enough debug information. So this unwind handler will be reading this debug information and saying, I know where these boundaries of the stack frames are, and I know where the objects are allocated, and I will call the drop descriptors correctly, right? So this is the job of an unwind handler. Roughly speaking, nothing prevents us from building this unwind handler in this operating system, which we are currently discussing, but it's kind of like tedious, right? So it's like a whole different, like a couple of classes to just do it, right? We can do it later, but for now we just say, okay, forget about it. If there is a panic, if you ask me what is this abort strategy, I'm not entirely sure. I don't know what will happen on abort. We can experiment. I never follow through, right? But essentially, when we say no unwind handler, it says, okay, forget about it. You don't have to implement this function, and we're good for now. Make sense?
Yeah. Okay. So any panic happens, we'll go to a panic handler, which I would believe is just looping
Yeah, which is
indefinitely.
yeah, exactly. So yeah, that's essentially you answer my question. So you'll go to the panic handler and we'll be just looping there. Most likely, more meaningful strategies to print something, reboot the system, or do whatever, right? But we don't do anything for now. But like later in your life, when you mature with this operating system, you can do something meaningful. We were probably printing some debug info to make sure that we can catch a bug.
Okay.
Make sense? And like, yeah, give me a second. I'll be right back. Sorry, guys. Like my nose is running. COVID gets me, although I feel pretty okay. But okay, sure. So back to Philip's thing. So the idea here is that at this point we will be able to compile everything what we need to boot, right? Like Philip talks about useful tools, right? Like this opt dump, disassemble. Read through this blog post. I mean, like Axel, send a link to the markdown. So this all can be read in markdown. I'm rendering locally. I didn't have time to make sure that it can be rendered through GitHub. I might do later, maybe I will fail. Just make sure that you read through this, right? But okay, sure. Now we have a file which, technically speaking, we can pass to the bootloader and boot on it, right? So at this point, Philip like he switches gears a little bit and he talks about the legacy BIOS format, like standard for booting, this master boot record, and that's exactly what we were studying in x86. Then in the last 20 years, people started gradually switching to this extensible firmware interface and unified version of it, so UEFI. It's more complex, stuff like that. But essentially, how he wants to boot is he kind of wants to jump on top of EUFI. What I will be doing, and I think it's sufficient for my purposes, is that we'll be using this multi-boot standard, right? So it's the thing which is developed by the Free Software Foundation, meaning that, it says it's an intermediate stage, and then as long as your kernel support this multi-boot standard, we'll pass control to you, and you don't have to worry about booting on a specific hardware, right? So, and as I was saying, essentially, what's needed is this multi-boot header, which you have to like put in the beginning of your binary. And then what Philip is doing, he talks about, I think it's own crate, so this bootloader API crate, which he's using. I'm not using it, right? So what I'm doing is that let me switch to this source code of this Hello OS operating system, and let's quickly look through the organization of the code. And this is how I suggest we're gonna implement our homework assignments for now. So, like again, so I took it from, I think most of it is taken from Philip, from his previous version of the blog post. Jafang helped me to update it to the current toolchain, so it's slightly more elegant. What happens here is the central thing is like Jafang has a README. He suggests that everything has to be done through Nix, right? It's easier for real, right? So he says, okay, install Nix. Then if you then type Nix develop, it automatically will get all the dependencies. The good thing about it is that just switch to this one. So if I do Nix develop and I'm on Mac, right? So which kind of like, okay, sure, I want to build x86 x86 executable on Mac, right? So my entire build, like my compiler toolchain has to be somehow maintained. That's a little kind of like annoying. With Nix, it's much easier. So essentially, he says, okay, use a Nix shell and you will be fine. And then if you do make run, it just whatever, just it satisfied all the dependencies and it prints the hello. It uses QEMU as an emulator. We can do something like make run no x. Then it will be using just a serial line, but it's the same, right? So it's convenient thing. So it's very similar to how we were using it in the undergraduate class, but this Nix shell, and if the func didn't screw it up, it should work on Linux as well, will simplify development a lot for you because it will automatically fetch all the dependencies like QEMU, all the compiler toolchain, everything, right? So you don't have to install Rust. Nix will do it for you, right? It's much easier. And then okay, that's just like a minor kind of deployment point, but like that's fine, right? So we understood this. README is there for how to build. The build is driven by the makefile, and at the heart of the makefile is that like in order to build the kernel, we will invoke cargo, similar to how Philip invokes cargo, right? But in order to boot the system, we will be using, we use here like this QEMU script, which runs QEMU for us. And we're passing an ISO image to the QEMU script. QEMU is an emulator which faithfully emulates different hardware architectures, but it does emulate x86, even on Mac, right? So it will essentially emulate an x86 machine for us. We pass a like ISO, like an image of an optical disk, and we essentially configure QEMU in such a manner that it says, okay, I assume that the grub is installed, and here we essentially just build, depending on whether you're on Mac or Linux, we either build this ISO from scratch, or on Mac, it's a little hard to build from scratch. So we have a pre-built ISO image, but essentially we just built with a specific grub bootloader installed, right? Or we start with a specific bootloader installed, right? So for example, when I say something like run, it just like says, okay, I depend on ISO and the kernel. ISO is either pre-built on Mac or it will be built from scratch from the files which you compile on Linux, and the kernel itself we build with Cargo. And then we run the QEMU-sh, like xv6 was just typing QEMU commands right here. It's a little cleaner and more elegant to wrap them in the QEMU-sh file, so just in a shell script. But like at the very end, what we're going to be doing, we will be executing QEMU, essentially 64-bit with all the arguments which we're passing here, right? And the idea here is that we, again, pass the ISO, right? And it, again, this is all just, it's either on Mac or on Linux. On Linux, you will be just passing one ISO file, which contains the kernel, and the grub bootloader is installed there inside that ISO, and this QEMU will try, it will run a BIOS itself, but it's part of the QEMU. We don't care about it, but this BIOS will read the master boot record from the ISO file. Well, this master boot record will contain parts of grub. Those parts of grub will dispatch the second stage of grub. The grub will say, look, there will be a menu which says, okay, which kernel to boot, but we auto-configured the menu to boot our kernel, and the grub will load our kernel, right? In order for grub to load our kernel, we need to say, look, the kernel has this master boot, needs to have this multi-boot header in front of it, right? Like I said in this in this drawing. Does this make sense? It's essentially, this is a public repo. You can open it anytime, but I'll post a link as part of the homework and everything, right? Again, at a high level, just a makefile. Makefile doesn't do much. It can start QEMU. Internally, it builds the kernel from using Cargo. I'll show you in a second how we compile essentially everything to make sure that we have a Rust kernel and a couple of assembly files which were linked together. And I'll show you how the linkage works as well. Make sense? And Philip does something similar, but I mean, he has a slightly different approach to it, and he uses more on, depends more on cargo than us, but it's okay. The thing which like again, cargo wants this file to make sure that this is where we put this panic strategies aboard. These are the crates we depend on, and okay, let's take a look. It's same stuff which Philip does. This is the another crate which implements spin locks, and this is the NASM, like essentially an assembler which we're using here. Okay, let's take a look. So in order to build things, instead of using make files like we did in x86, here we use a Rust build script. And again, it's just slightly more elegant, but at a high level, what this build script is doing, it says, okay, guys, I will add this linker script as a dependency. And this linker script is very, very similar to what we were using for building x86. So in fact, like almost identical. Let's go take a look. So it's inside src linker LD. So it's very similar to what we've seen in x86. So we say tell the grub that it starts at the first megabyte mark. So load the kernel there. Here we make sure that the very first, like this controls the layout of the binary, and we say the beginning of the binary will be this read-only data, which will contain multi-boot header. So the grub can take a look and say, look, I see it's the kernel, right? After that, we kind of say it's a text, data, BSS, GOT, PLT, like all the regular stuff. So nothing super interesting is going on here, right? Just make sure that all the sections are here. So okay, let me highlight it. The only reason we need this linker script is to make sure that we have this multi-boot header in front of everything else. You can process, like, you probably can do it mechanically, kind of like copy and whatever, adjust offsets and everything, but this just solves everything for us. So you just say everything will be linked correctly. The kernel starts at the first megabyte. All the symbols in the kernel are correct. This tells this specific directive tells the linker that the start is the entry point. So essentially, it will generate the kernel and says, okay, what's the name of the grub? The grub bootloader will know that it has to pass control to the start, right? Okay, but sure. So we say, look, this is the linker script. And this actually just simply says, okay, we depend on the linker script. So if it changed, please rebuild everything. Then it says, okay, please add these two assembly files. And those are kind of like the interesting ones. So the multi-boot header is nothing interesting. It's just a mechanical header, which you can copy from somewhere. It just like, this is the convention. This is, you say, it's actually standard number 2, multi-boot 2. It's essentially when the grub bootloader sees this header, it checks for this magic number. It says, okay, I see that you're a kernel. You need like size of the header, something else, some checksum that the header is not broken, but like don't really think about it too hard. What's interesting is that boot asm, and this boot asm contains this start label. So essentially, when our kernel, and this is the part which I was discussing here, so let me highlight it for you. So I will use this orange as a highlight. This is the part which is inside the boot.asm file, right? So it's very similar to our homework. So it has a global label start, since grub itself switches from 16-bit mode of execution to 32-bit mode of execution. So we will be running in 32-bit mode. We know it on top of grub. So essentially we instruct the assembler to say like generate 32-bit assembly. And at this point we can start like doing our stuff. And what we're going to be doing is we do a couple of checks. They're not strictly speaking necessary, but what's important, we're going to set up a page table, enable paging and segmentation, switch to 64. Segmentation is already enabled by grub, so probably you don't have to do it. So, but what you do here, you switch to the 64-bit, you load a 64-bit global descriptor table, and after that, you just jump to the long mode start. So it's a first function which executes in 64-bit mode. And if you where is it? Long jumps. Like if you go to this function, essentially it prints OK on a script, and this one invokes the Rust main function, right? Essentially, again, you can do it differently, and we'll talk about it more, so how to do it. But at a high level, set up a page table, and we'll talk about it. Just let me finish this lecture, and next time we'll probably talk about the page tables. But essentially, we're gonna set up a page table which uses huge pages, and then we will switch to a more normal page table later, right? But this Rust main function, essentially, if I just go back here, this is my Rust main file, like similar to how we discussed. I said no std, no main. I declare the panic handler, which just simply loops. I said that it's a cextern no mangle function. This is my Rust main, and that's why I can actually invoke it from assembly, because this is the calling convention is C, although I'm not passing any arguments, so like sure, but still calling convention is C. So essentially, before calling this function, I will set up a stack. So here, right, I just load it in the ESP register, and then it becomes RSP in 64-bit mode, and the stack top is just like some amount of bytes which I allocated somewhere here, right? So it's a very small like stack. So it's 4x4, 16 kilobytes, right? And again, like just to start, right? Make sense? Let me stop here quickly. So what I'm like, again, just to put it back in perspective, we used to do it with make files in x86. Now we're using this Rust build script. It's a little bit more elegant. Make files are a pain in the butt. We still use makefile to start everything and stitch everything together. I don't know, maybe it's a habit, but this is essentially the build script. Here we said, okay, the build script is very simple. We track dependency on a linker. We add 2 assembly files. And what we're doing here, every time we add a new assembly file, we create this a NASM. This is where we need this NASM crate, right? So we say, sure, you're going to be compiling this assembly file into an object file. And by the way, you will be compiling a 64-bit x86 executable, right, object file. And essentially, in the end, what we're going to do here is just we add those to the cargo, essentially because we use cargo, remember, to build the everything. In the end, we use cargo, right? So we said, okay, please add this, whatever the object file we want to get here, add it as a link argument, right? And again, I don't know where you are with reading about Rust, and it's not very important. So like this tool chain, I mean, it's nice and elegant, and I'm not an expert. I can only use it by example, but essentially everything is reasonably simple right now, right? And in the end, let me just duplicate this top again. Like in the end, when we invoke cargo from this makefile, when we build the kernel, it will use our build script, right? And essentially it will compile those assembly files first and compile the main.rs and other Rust files, and then link everything together. And it will be using our linker script. And typically one way to say use a linker script, you can pass it here as an argument. What Jafunk is doing instead is he says, okay, look guys, wait, where's my target? What I will be doing is that this is, remember I talked about it, this is this x86 64-bit unknown that's non-target. So it's a bunch of arguments for describing to the Rust compiler what architecture the compiler is dealing with, right? And like there is like sizes of different type of, not an expert what it means, but like little or big endian, architecture name, pointer size, stuff like that. No OS. Philip says that this OS none takes care of this. No, I forgot. It takes care of the panic approach. So right in this case, I think it worked, but I'm not sure. But remember, I said, how do we say pass the linker script to the linker? So you can also pass the pre-link arguments to the linker. And this specific argument says, okay, by the way, use this linker script. And that uses our linker script, which says, okay, like it's nothing special, but just essentially put the multi-boot header in front of everything, right? Another interesting thing which is worth noticing here is those flags. So essentially, those flags say that this architecture doesn't have extended registers, like vector registers and floating point registers, and instead tells the compiler to use this software emulation for floating point operations. Again, it's not a given thing for an operating system, but it's easier to start. So essentially, one would argue that operating, like the thing here is that normally Rust compiler leverages those extended registers to optimize like if you disassemble a Rust code, you will see a lot of MMX registers used just because they're faster than for some operation than integer registers. And sometimes you save the integer registers, you have more registers, stuff like that, right? When you're building an operating system, you have to take care of those. You have to save them and restore them on every exception, for example. You have to save them and restore them on every context switch, stuff like that. I would argue that the benefit of extended registers outweighs the difficulties of saving and restoring them. So in a real mature operating system, I would say, yes, use those registers. But again, just to simplify everything, we just start without them. And then maybe we'll talk about how to enable them and make sure that they're running. Right? Make sense? Okay, so any questions about the build system? I kind of understand that it's a little kind of fast and I'm switching between the files, but still just wanted to make sure that you have an overview, because I kind of recommend you to use this build toolchain. I think it's easier than Philip's, honestly, even to build everything, right? And this thing actually boots. So as I said, if I do make clean, that's essentially compiling everything. And what do I do? Run. Essentially just starts and prints hello world using QM as an emulator, but you very well can try to boot on real hardware. It should work. Make sense? Any questions? Okay, so what I wanted to talk about is the following. So we are very close, don't worry. What is this actually? So remember, and okay, hold on. So let me switch back to Philip's blog because it's a good time. So we were using up until now, I was using my self-hosted third edition of his blog, because those flags and how you use the environment to build everything alters slightly. Again, later on, Philip starts his own thing. He wants to boot on UEFI, stuff like that. I don't want to do it, right? So I'm switching back to essentially to the second version of his blog post now, to make sure that we switch back and it will correspond to the code which is in my code base. So roughly speaking, what we discussed already are these two blog posts, a freestanding Rust binary and this minimal Rust kernel. Philip doesn't use this assembly files in front of the Rust underscore main function. Instead, I assume he uses his bootloader crate. I mean, I don't see a reason to use another crate in this specific case, because with my assembly files, I can explicitly control how environment is set up. I don't need to depend on anything, on any third-party crates. I can change what's going on, but probably the most important advantage why I would want to push it is this thing that when we will be bootstrapping other CPUs, because we're going to be booting on multiple CPUs, instead of just like start function, we can, I don't have it in this code base, but we will be using a function which is very similar, which starts essentially start other CPUs, like essentially sends an interrupt similar to how x6 does it. And just essentially, it's much easier to do it this way. Just give me a second, guys. Okay, makes sense. So that's essentially the main logic, right? But what I wanted to talk about is essentially even in my code base, right? So when you see a main function, essentially I can print those lines. I use a print line macro, and it prints hello world from Rust, right? The question is like how to implement this this macro. Again, what you do here is that since there is no, like, you need a function to print something on a screen, right? And I'm following essentially the code from Philip, and in his second version of the blog post, it's covered as this VGA text mode. What he does is essentially he discusses here how to print something on the VGA screen, right? So VGA is this standard, it's implemented by the BIOS. It essentially allows you to print a character. You can pass a color. It can be has a specific background, but essentially it just converts to a specific letter on the actual whatever for the actual hardware, right? And essentially what he does is he says, look, guys, I will teach you how to build a tiny little thing which prints something on the VGA frame buffer, right? So he defines those colors. I don't want to go into the details because it's like I will ask you to read it as part of the homework, so we don't have to spend time. But essentially he talks about how you implement those different classes. I guess essentially a screen is a buffer of 25 by 80 characters. He talks about how to initialize this buffer. It's a couple of interesting details here related to Rust. And specifically the fact that you have to use this volatile crate because technically speaking, compiler can detect the fact that this data structure is not used because you're simply writing into it, and so it can be optimized out. It's similar to volatiles in C and C++. Essentially, you have to label those data structures as saying, okay, do not optimize out. That's one interesting bit, and he adds this volatile crate. But the other interesting bit is that he uses this lazy static initialization macro because in Rust, all the static variables have to be statically evaluated and initialized. And specifically, like it's not like in C, there is no uninitialized state, right? So here everything is initialized. However, in this specific case, Rust struggles with this, although technically speaking, it can support the static initialization of this specific code sequence. It struggles, and instead, this is initialized at runtime. So I don't exactly know how lazy static is implemented, but one would guess that it has a flag saying, okay, the very first time you try to access it, please initialize at runtime, and the next time you just access it, right? So essentially you have to wrap it into this lazy static. Another interesting detail in this code is that since this is a static variable and we want it to be mutable, so essentially Philip wraps it into a mutex, right? And it's a correct way to do it. So essentially it says, okay, so in order to get a mutable reference to this variable, you'll have to acquire a lock of a mutex, right? And this will give you a mutable reference, and then you will be able to write on the VGA frame buffer, right? So, and finally, he talks, and this is kind of like almost cryptic, but he says, okay, guys, we will define our own print line macro. Internally, this print line will be using like an underscore print function, and this underscore print function was essentially will be printing something on the screen, right? And essentially, this is exactly what I'm doing in my code base here. So I defined those macros. I copied it from Philip. I do print at the same time, similar to xv6, I print both on the VGA screen with this writer, and I'm also printing on the serial line with the serial one, right? And I essentially, and I think this code comes from Philip, if I remember correctly, from previous versions of his blog. So essentially, I have, similar to Philip, I have this VGA driver. So essentially, it's kind of like a very simple driver, right? So because it can scroll the strings and everything, right? It knows the colors, it knows what the hardware expects. Essentially, it takes a byte and then prints it like in a specific region of this VGA memory mapped IO, which the graphic card picks up, right? So I use this lazy static here to initialize. It's wrapped in a mutex as Philip suggests. And in order to print on a serial line, a second part of this essentially very similar to how xv6 was built. So it's initialization of the serial line interface, essentially just whatever follows the protocol, but in the end, it just like sends characters one after another on the serial line, right? And essentially what happens is that when I use a print line macro, it prints both on VGA and on a serial line. It shows up in both. And that's why I can boot and start my machine without a graphical interface, which kind of makes it easier to debug everything. And for us, it makes it easier to grade because then we can check the output of the serial line and see, okay, what's there, right? Okay, so I will actually update the website, so I promise. I will put the links to those blog posts and I will ask you to read them to make sure that you understand what's going on with the source code. I will update the source code slightly, or maybe not even like, it can be unupdated, and it will be essentially, your first homework is to essentially understand what the source code is doing and like essentially kind of, like you say, implement from scratch, but really everything is publicly available, so you can, roughly speaking, take it. But just, I would still argue, assemble it with your own hands, one by one, even if it's copy paste, you know, by debugging the build system and everything, you will catch a couple of errors and you will understand everything a little bit better. Everything what Philip publishes is also available publicly, so you can look at his solutions as well. And that will be our first homework, so which I will assign soon. But essentially, boot into Rust is the first thing. And then next time we'll start talking about how to set up the page tables, essentially, and start talking about the memory allocator, which we want to build. And essentially, like, your second homework will be to essentially, and this code will not be given, you have to build it yourself. Maybe it's available from Philip. But you will be essentially initializing the page table and a memory allocator. But let me stop here. So are there any questions? Okay, then good. Thank you. So Wednesday will also be virtual, just to make sure that I will not pass my COVID to anyone. So let's meet on the same Zoom. And then hopefully next week after that, I think Monday is a holiday, so but we're gonna meet in person on Wednesday. So thank you so much. See you guys. Chat. Thank you. Okay, see you guys.